How's it going, everyone? So welcome to our first lecture in this course, NSC 139. This is Science for Elementary Teachers. Let's just give a brief introduction about what this course is. Not really how this course is running in terms of structure, but really, why are we taking this course? Why am I teaching this? So children are naturally curious, right? They are, from the moment they're born, they're picking up things, they're touching things. They want to learn about the world around them. It's a natural instinct. And hopefully, as a person who's taking this course, you are the same way. You still have that natural curiosity to learn. You might not want to be a science major. You might not want to be a professional scientist, but hopefully, when you see something and you're curious about it, you want to learn more about it. I think most of us are. I think that's something that's really something about humans in general that is very unique, obviously. Um, but why is it so important to figure out how to teach scientific learning? Well, the reason for that is, especially if you are a United States citizen, it's a little concerning when you look at, now this is slightly old data, this is from 2013, but I can assure you that this data stands up to this day. We, as United States citizens, our students are lagging behind the rest of the world in their science education. If you take a look at this graph here, here is the United States, and we are performing around average, or just basically average, when that's the Organization for Economic Cooperation and Development. This is just like 34 developed countries around the world. Their average, we are right around that, if not below average in some aspects. Including math, by the way, is a big struggle for us. And then we've got other countries that are well ahead of us. Um, Now, the reason that is concerning is because in order to proliferate an economy and do all the things that supposedly make a country strong and great, you need scientists. That's just the bare bones facts about it. You are going to need engineers, you're going to need biologists, you're going to need physicists, you're going to need chemists. And basically, what you'll see a lot is we are having to import a lot of scientists into this country that are, because we are struggling in that aspect of producing new scientists. And so this is why it's so important that we figure out and create not only scientists, but we create teachers who are able to get students interested in these topics so that they can go on and in their secondary educations pursue these as careers. And so it's really important as teachers, if this is something that you want to do, that we learn how to have quality dialogue about science. Why would you want to study science? Well, even if you're not going to be a professional scientist, you're not going to be a biologist, and you're not going to be a physicist or a chemist, keep going on the list, engineer, the same critical thinking process that scientists use is a tool that you can use in your everyday life. In fact, you really need to be in order to make informed decisions. If you understand science, it can help you take better care of your health. Should I smoke? Should I not smoke? Right? Should I drink all the time? Should I not drink all the time? How can I eat a healthier diet? You could be a wiser consumer. What car should I purchase? What's going to be the cheapest per year? Things like that. Become just a better informed citizen, right? When it comes down to voting, when it comes down to being involved in your communities, being a critical thinker, being a scientific thinker can help you in all of these areas. You can use science to investigate a problem in your community, discover helpful solutions, and by applying scientific thinking to a problem, you're going to help yourself, you're going to help your community, you're going to help the world in general. And so it's really, really important. Obviously, you might not want to take my word for it, considering this is the career path I've chosen in science. But I promise you, it really is. And you know, I've also done some things in science where I myself have wondered is why is this important as I'm trudging through basically frozen landscape looking for birds. And then I have to realize that you are offering something that does increase our understanding of the natural world, and that's always helpful in some way. And so if that's not something you're going to do, think about all the things we just talked about as other reasons why scientific thought is very helpful. So here are some major unifying themes of science. The first is conservation of energy. We might talk about this later, but basically, I want you to keep in mind that energy, the thing that does other things, energy, it cannot be created and it cannot be destroyed. It can only be taken from one form and put into another. Here's a really quick example. If I hold this knife and I hold it up high, it has what's called potential energy. It has the potential to do work. If I drop it, it is then transferred, that energy of potential energy is transferred into the movement energy, which is called kinetic energy. And this is just not something that you need to remember right now at all, but I didn't create that kinetic energy. I transferred it. I put energy into lifting it and dropping it. That energy is transferred. It is not created and it's not destroyed, okay? Classification, of course, we can classify animals, we can classify other organisms, we can classify chemicals, we can classify anything. Classification is a major theme in science. A huge one, especially in biology, I'm a little bit biased, is the relationship between form and function. Why does a wing float on the air? Why are stingrays flat? Millions of things I could come up with. But form and function are intimately related. If you change something's form, you're going to change its function. If its form gets changed enough, it won't be able to do its required function. Here's an example. Have you ever wondered why having a high fever is so dangerous? Well, the reason for that is you have special proteins in your body called enzymes. And those enzymes, what they do is they speed up chemical reactions. Chemical reactions that are absolutely necessary to life. And without those enzymes would take hours or days to complete. You need them done in minutes, seconds. So if your temperature increases, your fever, those enzymes actually lose their shape. It's called denaturation or denaturizing. And they lose their shape. And if they lose their shape, they lose their function. And that actually can be deadly to you. And so that's just something to think about, the relationship between form and function. These themes interconnect the various scientific disciplines. That's what connects physics and chemistry and biology and tons of different ways in which we study science. Those three things very, very important to all of them. What are some characteristics of scientific knowledge? Well, the first is reliance on verifiable evidence. Contrary to what some people might think, scientists aren't just sitting in their labs and making things up because it benefits them in some way. No, all things in science have to be verifiable, they have to be reproducible, and they have to be real. Scientific fact is just that. It's fact. It's not something that's made up. Let me just clarify, good science, okay? There's obviously hack science going on out there that is obviously formed using some sort of agenda, but if it's verifiable, if it's irrefutable evidence, that is good science. By the way, this is just a little pet peeve of mine. Have you ever been watching maybe, I don't know, some show where somebody gets killed and they're investigating it, and the lead investigator, he comes on, he's like, oh, hold on, he goes like this. I've got a theory about that. Well, actually, he doesn't have a theory about that. In fact, you can't have a theory. I know that colloquial language, you can have a theory, but in science, you cannot have a theory. And it's not just a theory, okay? The theory of gravity, okay? That's not a theory. That's not just a theory. It is a theory, but it's not just a theory. A theory is something that is supported by years and years and years and years of irrefutable evidence. Look, if you want to bet me your life savings in your house and your car that gravity is not going to work, I'm going to take that bet 100% of the time. And the reason for that is we know it does work. We know that's how it works. The theory of evolution. I know that's a hot button issue for some people, but it's a theory. Science doesn't throw that word around, theory, very, very casually. What you can have is a hypothesis. A hypothesis is something that is basically an educated guess formed from various observations that you make, and then you make a hypothesis, an educated, well-formed guess. And that hypothesis is what you test. And anyway, I'm not going to get into the scientific method in this lecture. That'll be the next lecture. But just to point out that you can't have a theory, and it's not just a theory. Some facts, hypotheses, laws, and theories. What are they? A fact is a confirmed observation. We kind of all are kind of aware of what a fact is. The freezing point is 32 degrees Fahrenheit, right? That of water. Hypothesis, it's an educated guess. You make some observations, you put some information together, and you make a guess about something. That's a hypothesis. And like I said, we'll get more into that when I talk about, in the next lecture, the scientific process. What's a law? A law and a fact are very similar. A law is more in terms of descriptions of nature. And maybe we'll talk about what laws are. Laws are not so much used in all science backgrounds. Like biology, we don't tend to use laws. Physics tends to use laws, things like that. So it's a description of something in nature. And then a theory, like I said, it's a well-substantiated description. If you're ever curious, the theory of gravity. Do you want to bet against it? Probably not. I wouldn't. Predictions and testing, this is what science is. You make predictions like a hypothesis, a theory, not a prediction, a law, probably not a prediction. But all of those things, a hypothesis, theory, and a law, they are quantitatively testable. What does that mean? What is quantitative? It means that you can produce numbers, you can produce data when you're testing these things. And then testing itself does not prove or disprove, but it can give you evidence for or against. And once you have evidence against something, you can pretty much say it's definitely not a theory, and this hypothesis is probably incorrect. It does define a range of validity, and in my opinion, it probably does prove or disprove. Okay, once you show something over and over again is not possible, you can pretty much throw it out the window. Every law, theory of nature, it's subject to change, right? And it's always based on new observations. So some people might say, well, scientists were saying this about this one day, and then a month later they were saying something completely different. There's some sort of huge scam going on. Well, that's really just what science is in general. You are constantly making changes to your information based on the new information that you're getting. And obviously, when you're in something that's as in flux as our current situation with the current pandemic that's going on, when you get information one day, and it's very important to get information out to the country, to the world at large. When you get new information, it's important to get that out as well. And so, it would be irresponsible to not change your feedback when you get new information. Anyway, that's what science is: changing your information based on the new information that you get. Here are 8 science and engineering practices: asking questions, defining problems, developing and using models, planning and carrying out investigations or scientific scientific method. You're going to analyze and interpret data. We're going to do that in this class. You're going to use math and computational thinking. Sure, that's in every biology. Statistics is a huge part of biology and all sorts of other science. You're going to construct explanations and design solutions. You're going to engage in argument from evidence, not from opinion. That's a big one. And you're going to obtain, evaluate, and communicate information. And so with that, I'm going to leave it there. Hope you enjoyed this first lecture. Hope you're excited about this course. Just a little last part here. I'm not going to always put my picture up here in the top corner. I like to do it for the first one. But sometimes most of the time I'm just not going to put my face up there because I think it could sort of be distracting sometimes. But for this one, I thought, why not? And I'll see you in the next one, guys. Bye.